Hello and welcome to this clip on introducing ionisation energy. After going through what it actually is, we'll have a look very quickly at how it's measured and why trends in ionisation energy support the orbital model of the atom that we start teaching at A level. We'll have a quick look at what factors affect it and how successive ionisation energies for a single atom in an element can give us ideas as to what its electron configuration is and also what its identity is. And finally, we'll have a quick look at how to approach examination-style questions on this topic. And during this clip, we'll assume that you've already covered electron configurations using the orbital model. So this essentially means being comfortable with the idea of using electron configurations with S, P and D in them. So ionisation energy is the idea of removal of electrons. But it's a little bit more complex than just that, because you can have the first ionisation energy, or the second ionisation energy, or the third ionisation energy, depending on how many electrons you've removed. So to take the first electron off a neutral atom, the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to give 1 mole of gaseous 1 plus ions is called the first ionisation energy. Now within that definition there's several really important parts that you must actually include. So firstly, it's 1 mole of electrons from 1 mole of gaseous atoms to give 1 mole of gaseous 1 plus ions. So this is because the unit used is kilojoules per mole. Kilojoules per mole is the standard unit of energy that's used in chemistry. So the second important aspect of the definition is the fact it's gaseous atoms and gaseous ions. So because it's the energy to do with ionisation and nothing else, you don't want to have to spend energy separating out the atoms first before you remove the electrons. You want it to be the energy needed for one process only, and that process is the removal of electrons. So if we were to look at the second ionisation energy, in this situation we've already removed 1 electron, so look at the way the definition changes slightly. The energy required to remove 1 mole of electrons from 1 mole of gaseous 1 plus ions to give 1 mole of gaseous 2 plus ions. So the two equations that have been on the screen for a minute or so are basically the representation of what would happen for neon if it has the first ionisation and then the second ionisation. So it's important to bear in mind that you can only remove 1 electron at a time, so these two processes have to take place in sequence. You can't simply take 2 electrons simultaneously. You take the first one, and then you take the positive ion, and then take the second one. So the 3 things you have to be aware of that actually affect the value of ionisation energy is nuclear charge, distance from the nucleus, and electron shielding. So nuclear charge is obviously caused by the presence of the positive charge of the protons. Positively charged protons attract the negatively charged electrons in the outer shell. The further the outer shell electrons sit in the nucleus, the less they're attracted to the nucleus, so you get lower nuclear attraction. And the more shells that you have, the more shielding you get for the outer shell electrons, so they don't experience as much nuclear attraction. So what's really important to be aware of is how to word this. You're always trying to talk about the level of nuclear attraction between outer shell electrons and the nucleus. So nuclear attraction is a very, very important term to be using when you're describing ionisation energy and the factors that affect it, because essentially it's the nuclear attraction that controls whether the electrons can be removed or not. The stronger the nuclear attraction, the harder it's going to be. So looking at lithium, sodium and potassium in group 1. So going down the group, a shell is added each time, and therefore you get more shielding of the outer shell electrons. It becomes easier to remove one, even though you actually have more protons. So shielding has a very powerful effect on the ionization energy. So the key thing to remember is additional shielding decreases the ionization energy. So as you go down a group, the general trend is that the first ionization energy decreases due to extra shielding. This can be seen here from going from helium to neon to argon. So if you go along a row, the shielding remains exactly the same because there's no extra shells. So this time what happens is the additional protons in the nucleus as you go from one element to the next cause an increased nuclear attraction and therefore an increase in first ionization energy. So if we take the first row, first period, and look at it a bit more closely, the first ionization energy will increase overall. What also happens is the atomic radius decreases, and this is due to stronger attraction between the electrons and the nucleus. So you can see quite clearly how the number of protons increases, and that also increases the nuclear charge. And you can also see that there's the same amount of shielding because there's only two shells all the way across. So the trend is that ionization energy increases across the periods but decreases down groups, and you have to be able to explain this using the reasons given. So if we look at successive ionization energy, this is the removal of one electron after another from the same atom. And what it does is it gives us a clue as to how many electrons are in the outer shell. So if you look at the data closely, you'll see that the numbers, first four numbers, are relatively low compared to a relatively large number of 16,000. So we can deduce from this that the first four electrons must be in the outer shell. They experience similar shielding, so they're not particularly difficult to remove. The one at 16,000 will come from the next shell in towards the nucleus, so because it's closer to the nucleus, it's harder to take away. Let me try and demonstrate this. So this is your atom before any electrons are taken away. So to take one electron away, there you go, that's 786 kilojoules per mole. So you're now left with an ion. So you've taken away one electron, so it has one more proton than electrons. So when you get to your second ionization, it's going to be harder because you're removing one electron from a positive ion. So because the same trend would happen with the second, the third and the fourth ionizations, I've decided to skip them and go down to one of the blue electrons in the next shell down. This is where it's 16,000 kilojoules. Now you'll see here that there's no shielding, so much harder to remove this electron. So that big jump from here to here tells us that there's a break in shells at this point. So this is called successive ionization energies. These can also be measured by a mass spectrometer. Now, you may have come across the idea of a mass spectrometer that we use to tell us the isotopic composition of a mixture, for example. It can also measure how much energy it takes to remove electrons, and what this does is it gives us evidence for the orbital model as opposed to just the shell model from GCSE. So I should really change my title for this screen slightly, just to say successive ionization energy will be the energy required for removal of one electron after another from the same atom. So hopefully it illustrates now that to do this, it actually requires increased energy each time. I should technically tidy up my diagram showing the fifth ionization, so that would be a 4+ ion having an electron removed from it, so the fifth ionization would be of a 4+ ion. I've also just realised at the bottom right hand corner as well, I should have said skip 2 ionizations. Dear me, what am I like? I do apologise. So going from second ionisation, you skip 2 ionisations, then that takes you to the 5th. So if we look at the plot for the successive ionisation energies for chlorine, a steady increase, or relatively steady increase, in ionisations up to ionisation number 7 tells us that there's 7 electrons in the outer shell of chlorine, which is what we know from our work at GCSE. But you'll notice that there are little dips and troughs, and the dips and troughs are due to electrons in different orbitals. So these variations that you see, little undulations in the general trend, can only be explained by the orbital model, and they're due to things like shielding between subshells and repulsion between paired electrons in orbitals. So to show how ionisation energies give us evidence for the orbital model, you'll need to consider these two diagrams together. So I'm going to highlight boron, carbon, nitrogen and oxygen. So boron, carbon and nitrogen, if you look at the electron configurations using the box notation, what's happening is the electrons are actually moving into adjacent orbitals to one another. So what's happening is they're not experiencing any repulsion, so you get a nice steady increase in the first ionisation energy. But look what happens when you get to oxygen. So in the oxygen, you get 2 electrons that actually are now in one of the p orbitals together. It's highlighted in red. That causes the dip in ionisation energy. And it doesn't matter that there's an extra proton. The 2 electrons repelling actually make it easier to remove one of them, so the ionisation energy goes down. So let's now look at the dip from beryllium to boron. So if we look at the electron configurations for beryllium and for boron, what I've drawn is I've drawn out the box notations. I couldn't find a diagram that had the equivalent for these, so I had to make do with my one. So basically what happens in boron is within the energy level 2, you've got 2s2 and 2p1. So the 2p1 electron is shielded slightly from the nucleus by the 2s orbital. So what happens is you get a bit of a shielding effect. The 2s orbital is full, so it shields the 2p electron, the 2p1 electron, from the effect of the nucleus. So you get slightly lower nuclear attraction and therefore a decrease in the first ionisation energy. So it's a similar story with magnesium and aluminium. All that's happening is the same thing but one row down. So a similar shielding issue is going on here. So these little dips can only be explained by the use of the orbital model. This is why we need the orbital model, because it actually supersedes the shell model. It's not that the shell model is wrong, it doesn't give enough detail or doesn't provide enough explanation as to this evidence that we've now been able to get since the advent of mass spectroscopy. Righty-ho, so let's have a look at some practice exam style questions and how they might be approached. So moving the page down a little bit, it asks us to define the term first ionisation energy. So you can see that it's 3 marks, so you need to have all the essentials in there, like 1 mole, like gaseous, like 1+ ions. So let's move the page down a bit further and see what the next question wants from us. So this one is a 4-mark question, so it needs quite a lot of specifics and precision. So it says, state and explain the trend in first ionisation energy shown by the elements with the atomic numbers 2, 10 and 18. So if you have a look at your periodic table, you'll see that these atomic numbers, are elements descending a group. So because it's a longer answer style question, what I'd suggest is maybe putting it into bullet points, so you can actually construct your argument as you go. So the first thing to say is the first ionisation energy decreases. So the outer shell electrons are in a new shell. There's more shielding, so each time you go down a group, you add a shell. So the outer shell electrons are further from the nucleus, and despite increased proton number, the shielding has a greater effect, so the nuclear attraction is weaker. And the final thing is to pull these 4 points together and give them a context. And that context would be descending a group. So the construction of your question should take this type of format. You give a context, descending a group, you state the trend, you talk about shielding, you mention distance from the nucleus, you compare shielding or proton number, and then the overall effect on nuclear attraction. So I'll quickly do the first part of this question because it's fairly straightforward. So the key point here is you need to have a balanced equation plus the state symbols to show that you understand that it's all taking place in the gaseous state. So it says atoms of radium have a greater nuclear charge than atoms of calcium. So nuclear charge is essentially the same as proton number, isn't it? Because the only subatomic particles in the nucleus that are charged are the protons. The neutrons are neutral. So it says, explain why, in spite of this, less energy is needed to remove an electron from a radium atom than from a calcium atom. And again, it's 3 marks. So bear in mind that you may need to put some detail down here. The space would suggest so as well. Now, because radium is below calcium in group 2, the atomic radius of radium will be bigger than the atomic radius of calcium. So therefore, the outer shell electrons in radium are going to be further from the nucleus compared to their counterparts in calcium. So therefore, there'll be more shielding in radium compared to calcium. And just to be on the safe side, I've also added that there's less nuclear attraction in radium for outer electrons. So because it's a comparative question about 2 different elements, you have to compare the factors that we've discussed. The atomic radii, distance from nucleus, shielding, and nuclear attraction. So let's have a look at this question. It actually asks us something similar to what we wrote earlier. It's never too many times you could practice your definitions. So let's see if you can do this one yourself. Pause the video clip, see if you can jot it down, and then come back and replay when you think you got it. We'll see if we're in agreement. So let's now have a look at the next part of the question. It says, explain why the first ionisation energy showed general increase across period 2. Going from lithium to neon. So they're asking you to consider the fact that you get a general increase. Now they're not talking about the individual dips that we've discussed earlier. It's more the general increase across the period. So the increasing nuclear charge or proton number across the period, but the same shielding means an increase in nuclear attraction as you go. So those 2 points are your 2 marks. So the mark scheme, the first one, we got the idea of removal of 1 mole of electrons. But our definition also mentioned gaseous 1+ ions. So we said that the first ionisation energy decreases. The electron is in a different shell, and we mentioned further from the nucleus. So therefore there's more shielding, and we mentioned the shielding effect being more influential than the increase in proton number. So this leads to another point that the mark scheme didn't actually mention, but I think it would be good to put it in, is decrease in nuclear charge. Sorry, beg your pardon, decrease in nuclear attraction. I can't stress enough how important it is to mention nuclear attraction in the context of all these factors wherever you can, because it shows a thorough understanding on your part to the examiner of what's going on. So in the next question, we correctly identified first ionisation energy. We got the equation and we got the right state symbols. In the second part, we mentioned the atomic radius of radium is greater than that of calcium. and the outer shell electrons in radium are further from the nucleus than those in calcium. So therefore radium has more shielding than calcium and less nuclear attraction. So let's have a look at the final question. Now this is giving you the definition of first ionization energy in a slightly different way. It's saying the same thing as our version. It says energy change when each atom in 1 mole of gaseous atoms loses an electron to form 1 mole of gaseous 1 plus ion. So the key points are in there. It's just saying the same thing in a slightly different way. So we were still able to collect 3 marks there. The increasing nuclear charge of the number of protons is what we picked up, and we talked about the same shielding, which leads us again to the idea of greater nuclear attraction as you go across a period. So hopefully this has been a fairly useful clip to sort of introduce you to ionisation energy, trends in ionisation energy, and also to have a chance to have a look at some exam style questions and the types of answers that are flexible and accepted. So in the meantime, if you've got any queries or questions, jot them down and bring them into your teacher, or maybe come see one of us in a subject extension at college. So in the meantime, thank you for your time and see you soon.